Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section 1.5 on quadratic equations. Alright, so let's start off with what actually is a quadratic equation. You guys have seen these things before, I'm sure. A quadratic equation is an equation that can be written in the form ax squared plus bx plus c is equal to 0, where a, b, c are real numbers, and a is not equal to 0. So what that means is that not every quadratic equation looks exactly like this, but if you multiply it all out, combine like terms, and rearrange it, you can get it to the form ax squared plus bx plus c is equal to 0. And the other important thing here is that a can't be equal to 0. In other words, you have to have an x squared term. You don't have to have an x term, you don't have to have a constant, but you have to have an x squared term. Now it's also important to note that we're not going to be dealing with graphing at all in this section. We're going to be picking up graphing when we hit section 3.1 on quadratic functions later on in the course. All we're interested in here is solving these equations for x or whatever variable they might happen to be in terms of. Now there's only one type of problem in this section, solving quadratic equations. The tricky part to this section is that there are a bunch of different ways to go about that, each with their own pros and cons, times when they're better, times when they're worse. And so in total, we're going to be covering 4 different methods for solving quadratic equations: factoring, square root property, completing the square, which a lot of people have trouble with, but it's actually one of the stronger methods, and then the quadratic formula. So with that said, let's get started by talking about factoring quadratic equations. So the process for factoring a quadratic equation is pretty straightforward. Part 1 is it's important, very important, to move everything to one side and set it equal to 0. It has to be equal to 0. Once you do that, you factor the polynomial completely. Now if you're a little bit rusty on your factoring, it might be a good idea to go back and look at section P5 again, where we cover all of the techniques for factoring. Once you've fully factored the polynomial, then you have a product of factors equal to 0. And we're going to use something called the zero product principle, where if you have two things multiplied equal to 0, then that means either a is equal to 0 or b is equal to 0. We're just going to do that with the factors. So set each factor equal to 0 and solve. Now it's really important to note that that only works if it's equal to 0. That's why this first step is so important. If you've got two things multiplied together equal to 2, that does not mean that a is equal to 2 or b is equal to 2. All right? You could have 1/2 and 4, for example. This is something that only works if it's equal to 0. And then once you've done that, you usually just end up with two pretty simple linear equations to solve. All right, so let's take a look at a few examples. Try pausing the video here and see if you can find the solutions to parts A and B of example 1. So the way we go about factoring part A is going to be a little bit different from the way we go about factoring part B. It's already equal to 0, which is what we want to see, but anytime your constant is not there, anytime all you have is x squared and x, then all you have to do is the greatest common factor method. Pull an x out of both terms. So if I factor an x out of both, that just leaves me with 1x left over in the first term, and a 4 left over in the second term. So this is x times x plus 4 is equal to 0. Now we just set each equal to 0 and solve. So we get x is equal to 0, or subtract 4 from both sides, x is equal to -4. Now, a common mistake students make when they're dealing with a problem of this type without a constant term is that they'll try to divide an x out of the equation. The problem is that if you do that, anytime you divide variables away, you risk losing solutions. So you would end up with x plus 4 is equal to 0 if you did that. You would get the -4, but you would lose the 0. So never divide variables away carelessly. Part B is a bit more traditional, although it has a bit of a trick to it. First things first, it's equal to 6. That's not what we want to see. So we need to subtract that over to the left so that it's equal to 0. Now you could try factoring this as is, but if you notice that every term has a common factor, these are all even numbers, you can make your life a little bit easier by reducing the problem that you're working with. Divide both sides of the equation by 2. That will divide into all 3 terms on the top. And it will give us a quadratic equation that is a little bit easier to factor. So we're looking for 2 things that multiply to give -3 and add to give -2. We are looking for a -3 and a +1 in this case. Always double check. If I refoiled, this would be x squared minus 3x plus x, which would be a minus 2x minus 3. So it checks out. Now I set each of those equal to 0 and solve, which would turn this into a +3 and a -1. And as always, do keep in mind that anytime you're solving equations, you can always double check your answers by plugging them back into the original equation and making sure that it works. This is very valuable if you have a little bit of time left over at the end of a test. Let's take a look at one more problem involving factoring. And again, common mistake when students see this, I'll quite frequently get y minus 3 is equal to 30, y plus 4 is equal to 30. That doesn't work. If you want to solve a problem like this by factoring, you need to get it into the form ay squared plus by plus c is equal to 0 first. So that involves multiplying everything out, combining like terms. So I'm actually going to need to FOIL these 2 on the left. So if we distribute through, we get y squared plus 4y minus 3y minus 12 is equal to 30. And so now I'm going to start combining everything together. Y squared, 4y minus 3y would be a 1y. And then when I subtract the 30 from both sides, we would have a -12 minus 30, or a minus 42. All right, so now we can factor. I'm looking for 2 things that multiply to give a -42 and add to give a +1. So that's going to be a +7 and a -6. All right, and now just set each equal to 0 and solve, which essentially just flips the signs. Subtract 7 from both sides, add 6 to both sides, and we get y is equal to -7, or y is equal to 6. All right, so let's talk pros and cons. Some of the advantages of factoring is that if you get good at factoring, it is by far the fastest way to solve a quadratic equation if it's a nice quadratic equation. It's also the go-to method if there's no constant term, because then you can just use the greatest common factor method and solve the problem very quickly. The cons is that it does take practice with factoring to get fast at it. Otherwise, you might have to sit there and think about it for a long time or do a little bit of guess and check. And the other downside is that it doesn't always work. Not every quadratic equation is nicely factorable. There's actually a theorem in math that says that all quadratic equations, or all polynomials actually, are factorable, but you don't always get nice integers when it happens. And so factoring those the way that we did part example 1, just it's no good. So next up, let's talk about the square root property. The square root property says that for any real number k, if you have an equation of the form u squared is equal to k, and I wrote it as u because it could be some entire expression squared, so something like x plus 3 quantity squared is equal to 4, then this is equivalent to u is equal to plus or minus the square root of k. So a lot of times we think of this as taking the square root of both sides of the equation, but the square root property says that if you do that, you cannot forget the plus or minus sign on the side with the thing that is not squared. All right, very important, because you should get two solutions from doing this due to the plus or minus sign. So let's take a look at some examples involving the square root property. So in example 2, we're asked to solve the following equations using the square root property. Parts A and B are pretty straightforward. Just get the x squared on one side, the constant on the other side, get the x squared completely by itself, and then take the square root of both sides, but don't forget the plus or minus sign. So with that said, try pausing the video here, see if you can find the solutions to parts A and B of example 2. All right, part A, all you have to do is add the 5 across to the other side. Take the square roots, apply the square root property. So x would be equal to plus or minus the square root of 5. That's two answers, negative square root of 5 and positive square root of 5. But just leaving it as plus or minus is fine. B is just barely a little bit more work, although we do have to be careful here. If we subtract 16 from both sides, we have 2x squared is equal to negative 16. Divide by the 2. If we apply the square root property now, we get x is equal to plus or minus the square root of negative 8. We talked about how to handle something like this in section P7. This would be the same as plus or minus I times the square root of positive 8. But we can even go a little bit further because 8 is 4 times 2. You can take the square root of the 4. So you get 2 square roots of 2. And remember the I goes in between. So your two answers here are plus or minus 2I square root of 2. What this really illustrates is that if all you have is an x squared term and a constant term, so there's no linear term or x to the first power, the square root property is the go-to method. To show that this works for expressions beyond just x squared, let's do the same process for part C and D of example 2. So try pausing the video here and find the solutions to these equations. So for part C, we've already got the squared expression on the side by itself, so we can go straight into taking the square root of both sides. And so on the left-hand side, the square root would just cancel out the square, and we would be left with just the x minus 3. And on the right-hand side, we would have plus or minus the square root of negative 20, which again, let's simplify. So square root of negative 20 would be I times the square root of positive 20. And since 20 is 4 times 5, that would be 2I square roots of 5. This is plus or minus 2I root 5. Now we're not quite done yet. Our final answer needs to be x is equal to. And right now it's x minus 3 is equal to. So the last thing we need to do is just add 3 to both sides to get x by itself. Do be a little bit careful here though. Whenever you isolate x after applying the square root property, put anything else in front of the plus or minus sign, because this part should not be plus or minus. So if I add 3 to both sides, this would give me x is equal to positive 3 plus or minus 2I root 5. Again, just to really drive home the point, it's important that you know that this is two separate answers. One is 3 minus 2I root 5, and the other is 3 plus 2I root 5. Part D is pretty similar. Once again, we already have a expression squared isolated. So if we take the square root of both sides, it would cancel out the square on the left. And on the right, we would get plus or minus, don't forget it, square root of 4/9. This actually works out nicely for us, because remember, from square root properties, these are just exponents. So radicals distribute across addition and division, or excuse me, multiplication and division. So this would just be square root of 4, which is 2, over square root of 9, which is 3. All right, we're not quite done yet. We need to get x by itself, so I'm going to add 2/3 to both sides. But I'm going to put that positive 2/3 in front of the plus or minus sign. And now up here, it was fine to leave your final answer as 3 plus or minus 2i square roots of 5, and that's because due to the I and the radical, you could not simplify this really. Even if you broke it up, that's as good as it gets. There are no radicals here, there are no i's here, so you are expected to break this up and simplify. So our first answer would be x is equal to 2/3 minus 2/3, which would just give us 0. Your other answer would be 2/3 plus 2/3, which would give us 4/3. So our solution set here, our two solutions, are 0 and a positive 4/3. So let's talk pros and cons of our second method, the square root property. The pros are, well, we discussed this earlier, it's the go-to method if there is no x term to the first power. All right, you just isolate the x squared, take the square root of both sides, don't forget the plus or minus sign. And so because of that, it's very powerful under certain circumstances. In addition to that, once we start talking about completing the square in a second, the square root property is a portion of that process as well. The downsides to the square root property are mainly that it doesn't always work. And so if it doesn't, you can't use it. Otherwise, it's really good. It's not so useful for a full equation of the form ax squared plus bx is equal to c. So this brings us to the method that most students seem to dread from this section, which is completing the square. And I guess it's only difficult because there's so much to remember from it. It is a process, but honestly, if you can remember the quadratic formula, which most students seem to be able to, remembering completing the square is about the same level. So let's talk about the process of completing the square, and let's go through it. Step 1 is we're looking for a very specific form here, and it's not the same as what we had earlier. We're not moving everything to one side and setting it equal to 0. We're specifically looking for an equation of the form x squared plus bx is equal to c. And so what I mean by that is you want to move all the constants over to the right, and you want the coefficient of x squared to be 1. That's important for this process. So if you have something like ax squared plus bx plus c, you would have to divide that coefficient through the equation to get rid of it first. All right. Once you've got this setup going, our goal is to add a constant to this two expressions on the left to create something called a perfect square trinomial, something that factors into something squared. And the trick is that it is b over 2, so you take the coefficient of the x, you cut it in half, and then you square it. And to keep the equation balanced, you add that to both sides. Once you've done that, because of this specific number that we chose, the left-hand side will always factor perfectly. X squared plus bx plus b over 2 squared always factors perfectly into x plus b over 2 quantity squared. So it's just x plus the thing in parentheses before you squared it, quantity squared. And then once you do that, you've got something squared is equal to a constant. It won't just be c anymore because you'll have added another constant over here to the right, but all of this still just combines to make a single constant. And then you just solve from there using the square root property like parts C and D of example 2. So let's take a look at some examples of completing the square. All right, so we're going to work quite a few of these, 4 in total, because again, this is the one that students seem to be a little bit rusty on the most. And starting with part A, we're going to solve by completing the square. So to begin with, the first step is I'm looking for a very specific form. I need x squared plus bx, I'm going to leave a little bit of space, is equal to constant. So I'm going to subtract the 5 across to the other side. We'll have x squared minus 10x is equal to negative 5. The thing that I add to both sides is I take b, the coefficient of the x, the sign goes with it. So negative 10, cut it in half, square it. In this case, that would be a negative 5 squared, or a plus 25. And so what we end up with here is that this thing on the left always factors into the same thing. X plus b over 2, which was negative 5 in this case. X plus negative 5 would be x minus 5, quantity squared. You could double check. If you did x minus 5 times itself and FOILed it, you would see that it does in fact go back to x squared minus 10x plus 25. And this is going to be equal to negative 5 plus 25, or 20. And so now this is just a really straightforward completing the square problem. Take the square root of both sides. We would get x minus 5 is equal to plus or minus the square root of 20, which, because that's 4 times 5, would be plus or minus 2 square roots of 5. And then I just add the 5 across to the other side of the equation. Because there's the square root here, there would be no combining terms together. This is as simple as it's going to get. All right, so because this ended up a little bit messy, we ended up with radicals. This is a quadratic equation that you would not have been able to factor nicely. Factoring would not have worked on this one. So a lot of students will jump straight into the quadratic formula, which we'll talk about in just a few minutes. But with the quadratic formula, you oftentimes end up with really big numbers, and there's a lot of simplification going on. But honestly, this is a pretty easy and a pretty fast problem to work if you are comfortable with completing the square. All right, so now that I've shown you an example, try doing the same thing with part B, but remember, get rid of that 3 first in front of the x squared. So try pausing the video here and see if you can find the solution to part B of example 3. All right, well, first things first, like I mentioned, we're going to divide both sides of the equation by 3. Divide every term by 3. So we get x squared minus 2x is equal to 8. And again, I'm going to leave a little bit of space there. Is equal to 8. The thing I want to add to both sides of the equation is b, negative 2, over 2 squared. That's a negative 1 squared, or a positive 1. All right, now I factor. The thing on the left always factors into the same thing. X plus b over 2, so negative 1 in this case, quantity squared, and that's going to be equal to 8 plus 1, or 9. Now I take the square root of both sides of the equation, cancels out the square on the left. This is going to be equal to plus or minus the square root of 9, or plus or minus 3. Add the 1 across to the other side. No roots this time. I should simplify this. We're going to have a 1 minus 3. So that's an x of negative 2. And we're going to have a 1 plus 3, or an x of 4. So let's take a look at one more that's on the cleaner side, just for the extra practice. Once again, try pausing the video here and see if you can find the solution to part C of example 3. And so first things first, I'm going to move the 2 across to the other side with subtraction. So we get x squared plus 8x is equal to negative 2. The thing to add at both sides is b, which is a positive 8 this time. Cut it in half, square it. So that's a 4 squared, or a 16. All right, let me change the color of that just for emphasis. All right, so the thing on the left always factors into the same thing. X plus b over 2, which is a positive 4 this time, squared. And this is going to be equal to negative 2 plus 16, or 14. Square root property, take the square root of both sides. X plus 4 is equal to plus or minus the square root of 14. 14 is 7 times 2, so there are no perfect squares in 14. That does not reduce. And so last but not least, we just need to subtract the 4 across to the other side. Still put it in front of the plus or minus sign. So our two solutions would be a negative 4 minus the square root of 14 and a negative 4 plus the square root of 14. So let's work one more example, and this one is a little bit messier just because some fraction math is going to come into the mix. So once again, try pausing the video here and see if you can find the solution to part D of example 3. All right, so first things first, I need to move the 2 across to the other side again. So we get m squared minus 5m is equal to negative 2. I'm going to take b, negative 5, cut it in half, square it. B is an odd number this time, which is what makes this problem a little bit messier. But even still, it's probably not going to be quite as bad as you expect. So negative 5 squared, you can think of two ways. Either negative 5 halves times itself, or you could just square the numerator and square the denominator by property of exponents, however you prefer. Either way, that turns into a positive 25 over 4. So we add that to both sides. Now the left-hand side always factors into the same thing. X plus b over 2, which is a negative 5 halves in this case, quantity squared. And we do have to do a little bit of work to combine the constants this time. Negative 2 would be the same as a negative 8 over 4. So we've got a negative 8 fourths plus 25 fourths, which would combine to give a positive 17 fourths, because 25 minus 8 is 17. Now I'm going to apply the square root property. Take the square root of both sides. So on the left-hand side, it just cancels out the square, and we get plus or minus the square root of 17 over 4. By property of square roots, once again, square root of a over b is the square root of a over the square root of b. So this would be plus or minus the square root of 17 over the square root of 4, which is 2. And if you use completing the square on a problem that looks like this, your square root will always simplify nicely like this. This denominator will always be a perfect square, because the way you got that denominator in the first place was by squaring a number. Right? And then after that, the last thing we need to do is solve for x by adding 5 halves to both sides. So we get a positive 5 halves plus or minus the square root of 17 over 2. This works as an answer. If you would like to write this in the same form that the quadratic formula would give you, you could also combine these fractions together because they also always have a common denominator. This would be the same as 5 plus or minus the square root of 17 all over their common denominator of 2. So let's talk pros and cons of completing the square. The pro is that it always works for any quadratic equation, ax squared plus bx plus c, you can complete the square. It's not always nice, but it always works. Another pro is that completing the square is necessary for some other applications we run into, so just being familiar with the method in general is helpful. The other advantage, and this is the biggest advantage, is that even when it gets a little bit messy, if you get used to completing the square, that example we just worked involving fractions, you can still get that done and simplified faster than if you were applying the quadratic formula, especially if you didn't have a calculator handy. Now, the downside to completing the square is that it does have a lot of steps to it, and a lot of students have trouble remembering the b over 2 quantity squared. Again, if you can remember the quadratic formula, you should be able to remember that as well. That does mean, however, because there are so many steps involved, that does create more opportunities for careless mistakes. So with that said, let's take a look at the final method that we're going to take a look at for solving quadratic equations in this section. So last but not least, we have what's called the quadratic formula. And the quadratic formula is actually derived by performing completing the square, that same procedure, on the equation ax squared plus bx plus c. We just leave it abstract. We keep a, b, and c in place instead of plugging in numbers. And then we do the completing the square procedure. It gets a little bit messy because you have a lot of variables to keep track of, but ultimately it ends up simplifying to x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now it is important to note that because this comes from completing the square, this is specifically the solutions to ax squared plus bx plus c is equal to 0. Right? So if your equation is in any other form, you need to write it in the appropriate form so that you can correctly pick out a, b, and c. Right? Like, for example, a lot of times if I've got something like 2x squared plus 4x is equal to 7, a common mistake might be to say that c is equal to 7. It's not. Right? C would actually be equal to negative 7 in that case. So be a little bit careful. Once you do that, though, you just pick out a, b, and c, the quadratic coefficient, linear coefficient, and constant term, they're sometimes called, and you just plug them into the formula and simplify. Now, it is important to note that you will be expected to simplify your answers, right? Because you've got a lot going on in the square root. So at the very least, you need to collapse that down as much as possible, reduce as much as you can. So let's work some examples involving the quadratic formula. So I'm going to rewrite out the formula up here, but this is something you will be expected to know. Quadratic equations pop up in just about every math class ever. So knowing the quadratic formula really comes in handy. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so try pausing the video here and see if you can find the solutions to parts A and B of example 4. So starting off with part A, just jump straight into it. It's already in the appropriate form. B is the coefficient of x, so we've got negative 8 plus or minus the square root of 8 squared minus 4 times A, which is implied to be 1 in this case, times C, the constant term, so 12. And this is all divided by 2 times A, which again is 1. So I like to start by simplifying the stuff in the square root when working with the quadratic formula. Usually a calculator comes in handy with this because this is inherently a little bit messy. So 8 squared would be 64, minus 4 times 12, which would be 48. The difference between those two would give us 16. So this is square root of 16, but the square root of 16 is 4. So this is a negative 8 plus or minus 4 over 2. Because there is no square root anymore, you are expected to simplify this, break it up. So this is two solutions. We've got negative 8 minus 4 over 2, which would be a negative 12 over 2 or a negative 6. And we've got a negative 8 plus 4 over 2, which would be a negative 4 over 2 or a negative 2. So our two answers for part A are negative 2 and negative 6. Now, when your answers come out cleanly like this, that's a sign that this is a quadratic equation that you could have factored. This is one that you could have factored, but this was trying to get a little bit of extra practice with the quadratic formula. We were specifically asked to use it in this case. Part B is similar, so I'm just going to plug everything in. The numbers are going to get very large here because the coefficients are so big. So we get x is equal to negative b. If b is a negative 24, that's going to go back to being a positive, plus or minus the square root of b squared minus 4 times a, which is 16, times c, which is 9, divided by 2a, or 2 times 16. This time around, if you try to simplify the thing inside of the square root, you're going to find that negative 24 squared gives you a positive 576. 4 times 16 times 9 also ends up giving you 576. So this is a positive 24 plus or minus the square root of 0 over 32. But 0 squared is 0. Square root of 0 is 0. So that just goes away and takes the plus or minus sign with it, because 24 plus 0 is 24. 24 minus 0 is 24. So the plus or minus sign is not meaningful anymore. And so this whole thing is just 24 over 32, which if you divide both the top and bottom by 8, would give us a positive 3/4. Let's take a look at one more. So once again, try pausing the video and see if you can find the solutions to part C of example 4. So first things first, you've got to move everything to one side, set it equal to 0. It honestly doesn't matter which side you choose though. In general, I prefer my x squared term to be positive, so I'm going to move everything over to the right. So I got my 9x squared, subtract the 12x, the sign flips. Add the 5, the sign flips when you move it across. And now I'm going to do the quadratic formula. X is equal to negative b, which will take that to being a positive 12, plus or minus the square root of b squared. The negative sign always gets squared away in that, by the way, if there is one. Minus 4 times a times c, all divided by 2 times a. So let's start by working out the inside of the square root. So the negative 12 squared would give us a positive 144. The minus 4 times 9 times 5 would be a 20 times 9. So that would be a minus 180. And so if you subtract those two, you would get a negative 36. So this is a 12 plus or minus the square root of negative 36 all over 18. Well, square root of negative 36 would be I times the square root of positive 36, which is 6. So this is a 6i. So we have 12 plus or minus 6i over 18, but we can even do a little bit better because all of these are multiples of 6. So if I factor a 6 out of the numerator and the denominator, basically divide everything by 6, we get our final answers. X is equal to 2 plus or minus I over 3. All right, so pros and cons of the quadratic formula. Pros, much like completing the square, it always works. It's also pretty straightforward, and I think that's why students tend to gravitate towards this method so much. The downsides are that you have to memorize the formula, all right, and it's kind of messy. The other downside is that because you've got b squared and 4 times a times c, it's not uncommon to end up with pretty large numbers inside the quadratic formula. So honestly, it works best when you have a calculator handy. If you ever need to solve one without a calculator, things get a little bit hairier at that point. The other downside, which I didn't list here, is that I said one of the downsides of completing the square was there's so much going on that it's easy to make a careless mistake. The same is true here. I see it all the time where students try to apply the quadratic formula, they just miss a minus sign, they swap out a and b somewhere in the formula. It's very easy to make mistakes. So make sure you double check yourself when you are working problems with the quadratic formula. Even if your final answer is too messy to plug back into the original equation and check, once you've applied the quadratic formula, double check that you put all the right numbers in all the right places. So one last bit of information in this section, and this is not really related to any problems, but more a bit of information that can be gleaned, and that is the fact that the value under the square root in the quadratic formula, b squared minus 4ac, can tell you a lot about the solutions you're going to get out. And so it has a special name. It is called the discriminant of the quadratic equation. So the discriminant, again, is just the radicand, b squared minus 4ac. And in order to determine what's going on, all you have to do is think about what it means for the quadratic formula. So this is broken down into 3 cases. Case 1, if b squared minus 4ac is a positive number, then because the square root of a positive number is a real number, and because of the plus or minus sign, you end up with 2 real solutions to your quadratic equation. On the other hand, like part B of the previous example we worked, if the discriminant is exactly equal to 0, you end up with plus or minus the square root of 0. All of that goes away. So all that you're left with is negative b over 2a. So in that case, you just end up with 1 real solution. And then the last situation is like part C of the example we just worked. If the discriminant b squared minus 4ac is negative, then because the square root of a negative number is imaginary, and because the plus or minus sign is still there, you end up with 2 imaginary solutions. Or perhaps it's more accurate to say you end up with 2 complex solutions with a non-zero imaginary part. So solutions involving I. Now for right now, the discriminant only applies to number and types of solutions, but once we start talking about quadratic functions in section 3.1, this will actually correspond to x-intercepts as well. And so the discriminant will have an extra interpretation once we start talking about graphs of quadratic functions. All right, so that's it for section 1.5. There's really just one type of problem here, solving quadratic equations. It's just the method that varies here. So make sure you know the 4 methods: by factoring, by the square root property, by completing the square, and by the quadratic formula. Now that's it for this section, but I am going to have just a couple of minutes after this where I'm going to talk about some of the extra applications that come from completing the square, and one of those relates back to something we talked about in a previous section. All right, so first up we've got the idea of completing the square of an expression. So throughout all of chapter P, we were just working with expressions, no equations. And there are some applications that require us to complete the square of an expression instead. So we have to adjust our process just a little bit. So with an equation form, if we've got something like x squared plus bx is equal to c, we added b over 2 quantity squared to both sides to keep it balanced. The problem is there's no other side to counteract what we're adding in. So instead we use a different trick. We're going to add in b over 2 quantity squared, but we're also going to subtract off a b over 2 quantity squared as well. This has the net effect of adding 0, so it doesn't change the value of the expression. So the positive one will go into making the perfect square trinomial. The negative one will stick around and combine with the constant on the outside. So as a quick example, if we've got x squared plus 8x plus 5, that's going to be x squared plus 8x. I'm going to save the 5 for a minute, but it's not going anywhere. What I would add to both sides is b over 2 quantity squared, which would be 4 squared or 16 in this case. So I'm going to add a 16, but then I'm also going to subtract a 16 to counteract that, and we've still got the plus 5 sticking around at the end. These three will factor perfectly, just like with our equations, into x plus b over 2, so x plus 4 quantity squared, and then we just have a constant sticking around on the outside. Negative 16 plus 5 would be a minus 11. There's another trick we have to use if there's a coefficient in front of the x squared. With equations, we just divide both sides by a. We can't do that with an expression. So instead what we do is we factor out the coefficient. So 2x squared plus 12x plus 10 would be the same as 2 times all of x squared plus 6x plus 5. And then I'm going to complete the square inside of the parentheses. So this is going to be 2 times all of x squared plus 6x. The 5 is going to stick around again. This time what I add is b over 2 quantity squared, which would be 9. So I'm going to add 9, subtract 9, still with the plus 5. Those first three terms factor perfectly into x plus 3 quantity squared. But then we still have a minus 9 plus 5, or a minus 4. And then the last thing we do is we just redistribute the 2 through. And so this leaves us with 2 times x plus 3 quantity squared minus 8. And then finally, once we started introducing the equations of circles back in section 1.3, we said that they were of the form x minus h quantity squared plus y minus k quantity squared is equal to r squared. But what if that's already been FOILed out? Or what if you just have something like ax squared plus bx plus c plus some other numbers, say dy squared plus hy. So you've got first power variables as well. It's still the equation of a circle. You can determine the center and the radius by completing the square of each portion. So let's start with the x squared minus 6x in this example. And this is going back to being an equation, so we can add the b over 2 quantity squared to the other side. So for the x squared minus 6x, if we do b over 2 squared, that would be a 9. So I'm going to add 9 to both sides of the equation. And then if I take the y squared minus 8y and focus on it, I'm going to do b over 2 quantity squared, which would give us 16. So I'm going to add 16 to both sides of the equation. Then this factors perfectly into x minus 3 squared. This factors perfectly into y minus 4 squared. And the 9 plus 16 on the other side is 25. So this would be a circle whose center is at 3, 4, flip the signs, and has a radius of the square root of 25 or 5. All right, so that's it for the bonus slides on completing the square. As always, if you guys have any questions, please make sure you let me know, and I will see you in the next video.